We are going to begin our adventure in chapter 6. Well, yes, there is a chapter in our book. We are not going to use our book until like section 4, just so you know. Because slope fields are one of those things that I would rather you have a worksheet so you can actually like draw in the solution to the curve or actually put in the little slope. Okay? So the next few days we will have worksheets. I know that's disappointing. Okay? So I know that slope fields is something that we talked about last year, but we would like to talk about it again. What is a slope field?
A graph of solution curves.
Solutions to what?
A derivative.
Okay. So it's a graph of solutions.
All possible solutions.
I don't know if I'd say all possible.
Wouldn't that just be like black?
Yeah.
True. Or whatever.
We're going to call it a differential equation. Okay? We're not going to necessarily call it a derivative. We're going to call it a differential equation. Is that all right?
How you find tangent lines.
So, as you recall from last semester, right, you are going to get a differential equation, dy dx equals x squared, and we are going to take coordinates and we're going to plug them into our differential equation, and we are going to draw teeny tiny little tangent lines to represent each of these slopes at different points, right? That's basically what that is saying, right? So, if dy dx equals x squared, what is my slope at 0, 0?
0.
What's my slope at 1, 1?
1.
What's my slope at -2, -1?
4.
What's my slope at -1, 2?
1.
Please take the time right now to fill in all of your slopes. This differential equation only relies on what variable? X. So what's going to be true about our graphical representation? I would not use the word symmetrical. Okay, all of the X,
The Y's don't matter.
okay, the Y's aren't affecting these slopes. So anything that has a 0 for an X is going to have 0 slope. Anything with a 1 for an X is going to have a slope of 1. So this has a trend that looks like what? Cubic functions, right? And why does that make sense?
Because
It is 1 degree less. The derivative is 1 degree less than 1.
Okay, so the derivative is 1 degree less than the function. So if our derivative is x squared, then we know that our original equation is going to be 1/3 x cubed plus some c, right? And so these are representing all of those possibilities. Right? Excellent. So now let's talk about if we actually have to draw in a solution curve. Okay. So right now, y prime equals x plus y. Okay. You may want to get into the habit, especially when we talk about solving differential equations tomorrow. Y prime is the same thing as dy dx. So let's go ahead and fill in all of these slopes. Are you going to see a pattern? You kind of see a pattern diagonally, right? You should. Okay, now we've solved differential equations in the past semester, right? dy dx equals x plus y. That is not something we right now know how to solve, is it? Can we separate x and y with dx and dy? Okay, so a slope field right now is the only way we can really imagine our solutions, okay? So, first of all, there's one of the purposes, okay? We can't always find a general solution or a particular solution to a differential equation, so our slope fields are giving us the trend, right? So if I want a graph with the initial condition 0, 1, so when x is 0 right here, we need to follow these tangent lines to draw our curve, okay? I like, let the wind take you, okay? This is the wind blowing your curve, right? So where is this one gonna do? Go up, right? And then what has to happen as we go this way? Okay, well, first of all, we're gonna have to switch direction because we have a 0, we have slopes that are 0 and then slopes that become negative. So we have to switch direction, and then right here what's happening is it's acting like an asymptote, so we have to approach that. Okay, so we're going to do some prep. Any questions on that? I know right now this is review, so I'm not going to spend as much time on it. All right. So let's do some matching very quickly, and then we'll look at an AP problem, and then we'll look at our new material. Okay. So first of all, be careful with the directions. Right now I'm asking us to match the slope field with the equation of the general solution it could represent. Okay, so when we are matching a general solution that it could represent, we're looking for these graphs and how do they compare to this? My question is, how should we compare these equations to the graphs?
Derivatives of the equations. Match up values.
What?
Plug in a value into the derivative
Okay, so to get our slope fields, we plug in values into our derivatives. These aren't derivatives,
Yeah.
right? So these are the actual curves that we could be representing, right? So let's look at number 2. That looks like what kind of function? A cubic. So, which one of those does it match with? D. Be careful, what about number 1? F. It's a sine curve, right? We start at that 0, 0, go up. Okay. So this is what it looks like when you're matching a solution. It could represent, okay? You actually match the graph to its equation, right? Now, if we have graphs and derivatives, we have to think about what it would look like when we plug values in. So the first one I want to point out is this x right here. What is something we should look for to find the one that's dy dx equals x? Okay, our columns should all look the same, right, of x values. And which one would that be? What? B. Thank you. What is another strategy you can use in this particular case? Okay, we can plug in x values. We could also think of what's the antiderivative of x? 1/2 x squared. And so we know it should look like parabola. Okay? What's something else that anybody would like to point out as far as matching these up? Pick another one. Andrew.
With A, we have a line of zeros right where y would equal 2, so that's 3.
Okay, so A is 3. 3 is 2 minus y, so anytime y is 2, we're going to get zeros. All right, also notice how our rows, if you will, visually are the same. That means we're only relying on our y value. Awesome. Okay, another one.
The graph of F also has columns, so there's no y value. And you can see the general shape is an exponential going up. So that would be
And what's the antiderivative of e to the x?
e to the x plus c.
E to the x. It's plus c. Okay, so there are all of our e to the x curves. Okay? 3 out of 6. Let's go for another one.
E.
All right? E.
It's like the opposite of the one we just did.
Okay. First of all, notice how in diagonals we have a pattern, right? Anytime we're along the line y equals x, there's 0. So which one is it? B. X minus y. Whenever x and y are the same, their difference is 0. All right? How come we haven't talked about D yet? It's sine or cosine, right? In this case, we have...
The only option is sine, so it's sine.
Okay, fair enough. Which leaves C to be what?
2. Because it's the last one left. That's how you do it.
Thank you for adding to it. Okay. Questions? Okay, make sure you just really, you're going to get 2 different kinds of matching, whether it's matching to the general solutions or matching to the derivatives. So make sure you think about which one you're doing before you start going crazy. All right? Okay, so let's look at something you might see on an AP test. That's why we're in here.
Yay.
I'm in here because I like calculus.
True.
That too. Okay. So dy dx equals xy over 2. Okay. Now, this one I had to cut short because we haven't talked about finding solutions of differentials yet. That's what we're going to talk about tomorrow. So we're only going to do 3 parts of this problem instead of 4. So that's okay. So first, let's go ahead and fill out the slope field. an AP test, you will get 1 point for all of your zero slopes and 1 point for the other slopes. Don't ask me why that is. You guys tell me. How does that look? Okay, so what does our solution look like? Graphically, it looks like a bunch of what? Parabolas opening up or parabolas opening down, right? One or the other probably. Okay. All right, so in part B, we want to write the equation for the tangent line through 1, 1. So if we look at 1, 1, what is our slope? 1/2. So our tangent line is y minus 1 equals our slope of 1/2 times x minus 1. What's the answer from our test?
Yes.
It is, I think.
It's another slope's negative.
Oh, slope is negative. Shoot. All right, now we want to use this to estimate 1.2, or when x is 1.2. So y equals 1/2 times 1.2 minus 1 plus 1. What is that? Okay. Now, why do we use a tangent line to approximate this value? Why would we do that? We don't have the original curve, do we?
Yeah.
No. Okay. Well, biggest reason why we don't have the original curve. Okay. So we can't get there right now. And so, but if we know the tangent line, we know we can get close. Now, part C. How does it compare to the actual value? Is 1.1 an over or an under estimate?
Underestimate there because it's concave increase.
Okay. It actually doesn't matter if it's increasing or decreasing. If we look at the solution curve at 1, 1, right, we have a curve that is concave up, which means our tangent line is sitting below the curve. And so our y values are below the curve, and so it is an underestimate.
I mean, if we did want to do a solution, we could. We know how to do that.
Right. We could. All right.
But we're talking about tomorrow.
This is okay. Now, oh, Jared, you made me lose my train of thought. Okay. Now, since we have the slope field and we have a visualization, we can see that it's concave down because we can, or concave up, excuse me, because we can see the trend of our slopes, right? If we didn't have that visual, what would we have to find?
Second.
And do we know how to find the second derivative
Yeah.
of that? We would have to do so using what kind of differentiation? Implicit. Okay? And you would have to multiply by dy dx in there, right?
Yeah.
True.
Okay? And so we could do that, and if we did that, we would find that at 1, 1, our second derivative was positive, and so it would be a concave up, and so it's an underestimate. Okay, but with the slope field, we can have a visual. All right? Less work. Woohoo.
It's like putting on the slopes.
Right, but that's almost mindless work, right?
Yeah, but
I
then
mean-
it's so mindless that you screw up all the time.
Would you rather take that second derivative?
Yes.
Okay, then do it. All right, so let's talk about this tangent line thing, okay? How close does our tangent line get when we approximate values?
Depends on what the slope is.
It depends on the slope, and it depends on how far away you are from that point, right? Okay. It would be nice to have a closer estimate, right? There's also times where we're not going to be able to solve a differential equation, and so our only option is a tangent line. But those of you taking statistics, even though it is close, it's really not that close, is it? If we talk about like errors of percentage and all of that kind of stuff, right? Okay, so we want a way to approximate this even better. Okay, so instead of having a curve, having a tangent line, and walking along that tangent line, what we're going to do is we're going to break this up into little itty bitty steps where we're going to keep adjusting our tangent line. So we're going to start with the tangent line and move a little bit and find an and curve it along, not curve it because it's a line, but we're going to adjust our little tangents to follow the curve closer. Okay? So we're kind of like walking on a tightrope, okay, if you will. We're just going to,
It's not straight.
it's not straight, okay. We're adjusting these little itty bitty tangents to follow the trend of our curve, okay? How are we going to do that? Okay, first, we're going to start at our point, okay? We are going to calculate the slope of that tangent using our derivative, okay? Then, we're going to walk out just a little bit on our tangent line, and we'll do so and find that y value, okay? So I guess I kind of forgot to say we have to figure out how many steps we're actually going to take, okay? So we're going to have calculator slope. We step out just a little bit and we now have a new y value. And so from that new y value, we're going to reevaluate the slope, find our tangent slope, and then we're going to take another little step. And then we're going to take that new y value and we're going to find our new slope. And we're just going to keep kind of adjusting these little tangent lines as we move along. Okay? So I have this chart for you. Okay? We're going to fill this chart out for as many steps as we need to take. Okay? So n is going to be our number of steps, which means that's how many rows we're going to have here. Okay? Now, with each step, you're going to change, we're going to have a change in x. Okay? And we will calculate that based on where we're starting and where we're ending and how many steps we're taking. Okay, kind of like we did with Riemann sums, right? Okay, now, you'll see this funny notation right here. How do we find slope? Okay, so if I rearrange this and I multiply the change in x over, we have this, right? So after we figure out what our tangent line slope is, we're going to figure out what our change in y is and add that to our old y value to get where we're going to start for our next tangent line. Okay? So let's see how this is going to work.
Is this going to be like Riemann sum last year when we like did a very long dot
No.
method and then
No.
it's actually faster?
No. Okay? No. Okay, and I've been saying it wrong. It's Euler. I do that all the time. It's Euler. Euler's method.
No,
I like to say
Euler.
Euler, but it's Euler. Okay.
But all possible.
So the whole point is, okay, think about trying to, well, okay, so this one isn't a good one. This one on purpose, I picked one that we could find the actual solution to. Look at our second example, 2x minus y. We cannot find an actual solution to that one. We don't have an option other than using a tangent line to approximate. Okay? So, let's do this. How many steps do we want to take?
2.
2, and it's 2. We are going to begin at x is 0 and end at x is
Cinco.
x.
No, just kidding.
Okay, so our change in x, we want to end at 0.8. We are beginning at 0 with 2 equal steps. So our change in x for each of our steps is going to be what?
2/5.
Okay. So x, y, slope, change in y, new one. Okay.
Please excuse this interruption. Again, this is a reminder for students riding the bus. There has been a bus change this evening. Bus 10A will be bus 6A. Again,
So we start at 0, 5.
will be bus
What
6A.
is our slope?
Thank you.
-2.
-2. Now, to find the change in y as we walk along this tangent line, we're going to take change in y is just slope times delta x. So what is our slope times delta x?
2/5. 4/5. -4/5.
Okay. So if we begin at 0, 5, and we've now had a change in y of -0.8, our new y value is what along our tangent line? What? Okay. So I don't know what this looks like, but we walked out on our tangent line, let's say to here. Instead of continuing to walk, we are going to find a new tangent line that fits a little, it's probably not right on the curve, right, but it's fitting a little closer with it, okay? So now we have our x coordinate is at 0.4, 4.2. So now what's the slope on that tangent line? -1.6. All right, our change in y, we take our slope times change in x. Yeah, -0.64.
0.64.
Right. Okay. Our change in y should get smaller and smaller, right? Okay. And so what's our new y value? -4 what?
What? No.
Did I do something wrong?
Yep.
Should be 2.56.
I did it wrong way, didn't I? I forgot how to add.
It's okay. We'll forgive you. Okay. So now we've gone through Euler's method twice. We've reached our x value of 0.4. So y, no,
Yeah, we do. That's 2 steps.
now our new x value is 0.8. Our y value is 3.56. Okay. So now at y, evaluated at 0.8, our value is 3.56. Done.
3.7.
What?
3.7.
Okay, so if we would have approximated with a tangent line, we would have got 3.76.
No, 3.76 is the actual solution. Sorry.
Okay, if we used a tangent line approximation, we would have y minus 5 equals a slope of -2 times x. Plug in 0.8 to that. 3.4. This is a lot closer to 3.7 than 3.4 is. right? Okay. So those of you in statistics, you can do all of your error, the percentage, right? Okay, now, how could we make this even better? How could we make it even closer to the actual value?
More steps.
Okay, the more steps we take, the closer we're going to be to our actual value. So I do not believe we will have time.
Do we want an equation for doing all this tomorrow?
No.
You
See that?
No, I don't see it. What are you doing?
What are you erasing?
Okay, so in this one, we have 5 equal steps. Okay, so it's going to get even closer. All right. Now, also, I want you to notice this 2x minus y is our dy dx. We can't separate those variables to find a solution for, right?
Right.
Good. Okay, so Euler's method is our only way to approximate that solution. Okay. Cross-country runners, we hope you ran fast and you drank lots of water afterwards. Say bye.
Bye.